Okay, so this next chapter is all about graphing our trig functions. Now, we're going to start with sine and cosine today, and basically what we're going to do over the next couple days is just add on a new transformation every time. So we're just starting out with the basics of just what sine and cosine look like and adjusting like the vertical stretch and vertical shrink that goes along with it. But then from here on out, we'll just like our horizontal shifts or vertical shifts or period changes and so on and so forth until we get a function at the end with all of those transformations. So we'll just add on a little bit every time. But for the first part, we just have to discuss like what sine and cosine actually look like in a graphical sense. So we know what they look like on a unit circle. We've been looking at sine and cosine and we know the values as our theta increases. But in a graphical sense, what we're going to do is lay it out linearly. So what it ends up looking like is some periodic function, which this kind of makes sense because we know our unit circle has coterminal angles after you get to 360 degrees. It just repeats. So a periodic function in general is a graph that just repeats itself in a set cycle. And the length of that cycle is called the period. It's how long it takes to complete one of the cycles. Now for sine and for cosine, and in our general sense of just sine and cosine, this is called a parent function when it's the most basic form of that function. Our period, the length that it takes to complete one of our cycles is 2 pi, because that's how long it takes to go around the entire unit circle. Once we adjust, like this is not always the case, it can be adjusted, and we'll see that a little bit later. But for now, our period and our general sense is 2 pi because that's how long our unit circle is, or how long it takes to get from 0 to back to that starting point of our sine and cosine functions. And again, we know what it kind of looks like we know what it looks like on the unit circle, and you've probably seen sine and cosine graph before. But in a linear sense, it looks a little bit different than what you'd maybe expect. And there's some really cool graphics out there, so I'll actually post them on the website because I think it's a really good sense to see what those things look like and why it looks the way it does, and how those like values at those specific places actually correspond to what our graph ends up looking like. I used to have, when we did this before, I used to have kids like graph all of the values, but we're going to skip that this year so that way we can go right into more of like practicing and seeing how we can affect the period and the amplitude. Today we're just talking about amplitude, but anyway, how we're going to do it today is we're going to look at these critical values. Now there's always going to be 5 critical values when you're graphing your functions. For now, we're going to look at the quadrantal angles, and this kind of makes sense for our critical values for sine and cosine because those are the places where we reach maximums and minimums. So if I'm evaluating our x value, these are going to be all of like our input. So we're putting them into our function, and these are all of our output values. Remember, input values are all of our domains, and our output values are all the ranges that we're going to get. So once we look at our input values and our output values, we'll fill in our domain and range. We should actually know these, but we can at least remember what they are based on what we're inputting and outputting in our function. So I'm going to draw a unit circle off to the side because that'll help me kind of visualize what's happening here. If I'm looking at the sine of 0, I'm here on my unit circle, so my y value that I'm looking for, the sine of that function is actually 0. If I'm looking at pi over 2, I'm up here on my unit circle, my sine value is going to be 1. As I continue on, here I am at pi, my sine value is back to 0. At 3 pi over 2, I'm down here at -1. And at 2 pi, I'm completing my entire cycle, so I'm back here at 0. So I'm going to label this on my x-axis. So these are all, again, my x values of my theta values. So here's 0 and 2 pi here at the end. Halfway between that's going to be pi. We have pi over 2 and 3 pi over 2. Again, what we're doing is we're taking this unit circle and we're laying it out linearly so we can actually look at it on a Cartesian plane versus what we have more of when we look at it this way is in polar form, where we're actually looking at our theta values as we go along our unit circle. But this one, we're looking at our x values, and we'll see what this looks like. So our first function here is at 0, 0, our first point. And then at pi over 2, we're up here at 1. At pi, we are at 0 again. At 3 pi over 2, we're at negative 1. And at 2 pi, we're at 0. So when we actually connect our points, we shouldn't actually connect it in these straight paths because this is not a linear function. This is something that's curved. So we want to make sure that our connections to these points are in this curved way. And this would continue on forever in this direction and continue on forever in this direction. And we have this very curved periodic function, and all of your sine values and all of your cosine or sine functions and all of your cosine values will be in this general sense. So our domain are all the input values that we're plugging in. We can evaluate sine and cosine at any angle. So our domain is negative infinity to infinity. But again, the output values that we're getting, we can see that graphically now is that we're only oscillating between 1 and negative 1. We're not going beyond those values. So our domain or our range is 1 to negative 1. And again, this is called a parent function because it's the most basic. Once we look at the stuff that we'll look at in the next couple lessons, we're manipulating our parent function and changing some of these critical core values. There's still sine functions and there's still cosine functions, but we have transformations that happen from them. Okay, so we'll look at cosine now. Again, I'm going to draw a little unit circle off to the side because that will help me at least visualize what's happening. So at 0, my cosine is my x values on my unit circle. So if I evaluate cosine of 0, that value would give 1. At pi over 2, my cosine is 0. At pi, my cosine is negative 1. At 3 pi over 2, my cosine is 0. And at 2 pi, my cosine is back to 1. So looking at the difference here is we're just kind of alternating between 0 and 1 for all of my sine and my cosine values. So I'm going to label it the same way on my graph. Here's 0, here's 2 pi. Halfway in between is pi, and then halfway in between those values is going to be our pi over 2 and 3 pi over 2. And we have 1 and negative 1. Again, our period is 2 pi because that's how long it takes for us to complete one of our cycles to go all the way around our unit circle. So if I start at 0, my cosine value is up here at 1. At pi over 2, my cosine value is at 0. At pi, my cosine value is at negative 1. At 3 pi over 2, my cosine value is 0. And at 2 pi, my cosine value is 1. And again, I don't want to connect it in this straight path. This is not a straight curve, so we are going to connect it in this curved way. So we start up here. We kind of go down in this like bell shape. Oops, it's not very great. A little too curvy here. But that's the general sense and the general trend for our cosine value, or cosine function. Now if you notice, like if I could continue this on and on forever, because it's this periodic function, and if I just look at like this and analyze how these things compare, they really are pretty much the same function. It's just shifting over, which makes sense because I'm shifting over my 1s and negative 1s. So like imagine this table that I have shifted up 1, or this table that I have shifted down 1, and I would end up getting my cosine function or my sine function in this vice versa way. Again, our domain for this is negative infinity to infinity because we can plug in any angle value, and our range is negative 1 to 1. So we're going to deal with our first transformation today, and we are going to explore what sine x looks like. And to do that, you can explore these kinds of things on Desmos, but I'm just going to show you on my graphing calculator here of what regular sine x looks like if I graph it. And again, we just saw this. We saw like at least part of the function from 0 to our value here of 2 pi. My x-axis right now is not in radians, so our tick marks could actually change it for you. But just imagine these are normal x values. So 2 pi here is going to be at like 2 times 3.14159, so the 6.3 whatever. And then our x value here is at the 3.14, which is kind of, you can kind of see that on my graph. Here's 1, 2, and then 3. If we zoom in, you'll see it actually cross in at about that pi unit. So not quite at 3, but if I trace it here, oops, going the wrong way. We are crossing the x-axis at about 3.14159, which is that pi value. Anyway, just to kind of see what that looks like graphically, kind of interesting seeing on a calculator like that. So our first function here is going to be sine x, and then I'm going to plug in for my second function 4 sine x and see what happens. So the first one that's going to be graphed, we'll see, like we already graphed that as sine x, and the second one that's graphing now is the 4 sine x. So if I'm comparing these two graphs and deciding what I see, I'm going to zoom in. So again, this one is our regular sine, and this is our 4 sine. And the only reason I'm zooming in is because I want to see the difference between these two as far as my x values go. So like I zoomed in and saw that there was a 0 here with my regular sine function, and we can see in our second function it crosses at that same point. So the values of like the zeros that I have in my regular sine function, which happen at 0 and pi and 2 pi in on my graph here, are still the same zeros for my sine of 4x. The only thing that's happening, or the only change that we see, is that we're stretching it out and making it taller. So instead of actually going up to 1 and down to -1 on my function, my table, let's see if I can actually, so I'm going to start at 0, and I'm going to actually go in increments of pi over 2. You can kind of see that. The only thing that's changing, if I look at like this table versus, so this is the table we generated when we were looking at our regular sine function and plugging in and evaluating at the unit circle. We're getting that same thing, and obviously it's going to repeat because it's a periodic function. And the only thing that's changing is that my 1s are actually becoming 4s and my -1s are becoming -4s. So I'm taking that 4, which is literally on the outside of that sine, and I'm multiplying by sine. And what that does is it just makes my graph a lot taller. The same thing will happen with cosine. The same thing will happen if I multiply by a different value here, like 2 or 5 or 10. My function itself will just get a ton taller. So like if I did plug in, say, 10 sine x and graph that, here's my regular sine x. My next one will be the 4 sine x, which is taller, and then my next function that I'll graph will be the 10 sine x, which has the same zeros, we'll see, but it's just stretching out and getting a ton taller along my curve. Okay? So that idea of how far we actually reach up and how far we go down has a specific name. That's in the back here. That's called the amplitude, and that is our height from the center of the graph that I have to the top of my graph, or the center to the bottom. So for now, we have a standard form where we just have that multiplier on the outside, and we're going to call that A for amplitude. So the absolute value of A tells us our amplitude of our graph. If our A is greater than 1, that's what we saw here, it like stretched it out. So that's called a vertical stretch. Got an R. Stretch. And if A is between 0 and 1, so I'm going to show you, like if I did 1/2 sine x, so I'm going to go from 0 to, we'll say 2 pi, and I'm going to go from -2 to 2. So here's again my like regular sine x function. You can't see that very well. And then this is the next one that I'm graphing, which is the 1/2. So what that does is actually, instead of makes it taller, it makes it shorter. So, and that should kind of make sense because our multiplier is, you know, making it half as tall. So this is actually called a vertical shrink. And then if I take that, I'm going to erase this one. And I'm going to make my a value negative, so something that's less than 0. So I'm going to just use negative sine x. So again, here's normal. If I have a negative, what that ends up doing is it flips that graph, and instead of going like, here's our normal function where it goes up and then down and then up and then down again, our sine with the negative sine function is actually going down and then up and then down and then up. So what that does is it actually reflects it over the x-axis. The important part here is that we have our critical values to show when we're actually graphing, so we know where these zeros actually happen, and we know where our maximum and minimum actually happen. So on the front here, we needed like these 5 critical values to actually graph these important points, and we have to actually show it on our axis. Okay, so we're just going to practice a couple. So we're going to start with 3 sine x. We have our normal critical values when we're looking at that. So we've got 0, 2 pi, pi, pi over 2, and 3 pi over 2. Those are the normal quadrantal angles of our sine function and cosine function. At 0, and we're just going to go through this process. You can make a table if you want off to the side, but we're just going to go through the process of actually graphing. So at 0, my sine value is 0. So 3 times 0 is going to be 0. At pi over 2, my sine value is 1. So I take that multiplier outside and multiply it by 1, just like we saw on the table. Sorry, multiply it by 3, just so we saw on the table, and we'd have a value of 3. So instead of plotting it here at 1, we're plotting our y value at 3. At pi, I'm at 0 again. At 3 pi over 2, I'm going down, so I'm at negative 1, but then I multiply by 3, so I'm down here at negative 3. And then at 2 pi, I'm back to 0. So altogether, there's my sine, or 3 sine x function. Kind of missed my 0 here, or minimum. Okay, let's do another one. So same critical values that we're looking at. We have 0 and 2 pi, pi, pi over 2, and 3 pi over 2. Okay, I'm going to make this 1 and negative 1. So if I'm going to graph negative 1/2 sine x, the first critical value, if I plug in sine of 0, that's 0. Nothing to worry about. I also have zeros, so I can just fill them in right now. At pi and 2 pi, those don't change, because sine is 0 at those values. At pi over 2, though, my sine value is 1. And I have this negative 1/2 multiplier. So that means that instead of going in like the normal up-down fashion that I would graph my normal sine, I'm actually starting here going down because I'm flipping it over the x-axis. And that 1/2 will tell us my amplitude. Should have written that here. So my amplitude here is 3. My amplitude here is going to be 1/2. But I have a reflection over the x-axis, and eventually we'll make all these a list of all these transformations, so you might want to start now so that way you can keep track of it and make it sort of a habit. So I'm going to reflect over the x-axis. So I'm going to be here then at 1/2 going down. And then the negative, or the 3 pi over 2 is normally like negative values, but we're actually graphing it above the x-axis this time. And again, my amplitude is 1/2. So all together, looks like that. Okay, so again, normal sine and reflected sine. So instead of going up, then down, we're going down and then up. Nothing too crazy. Last one for cosine. Again, we kind of have our normal critical values of 0 and 2 pi and pi, pi over 2, and 3 pi over 2. I'm going to make a list of all my transformations. So I have this 4 out front, which tells me my amplitude is 4. That means that I'm going to go up to +4 and then down to -4 for my maximums and my minimums. I also have this as not just a 4, just a 4, but a -4, which means I'm going to reflect over the x-axis. So normally what we saw with cosine is that we start here at 1 and then we go down to some minimum, we go back up. So if we're reflecting over the x-axis, that means that this one is actually going to start down below. So we're actually going to look more like this. So I have zeros for cosine, I have zeros for cosine at pi over 2 and 3 pi over 2, so I'm going to plot those now, but you don't have to. And instead of starting up here at 4 and going down to my minimum and coming back up, I'm starting here at -4 for my 0. You could also just like kind of plug it in. Like cosine of 0 is 1 times -4 gives my starting value of -4. Same thing here, like if I plug in pi, cosine of pi is -1, -4 times -1 is +4, which is why we're plotting it up here above our x-axis. And then at 2 pi again, that's a coterminal angle with 0, so we should get the same value. So down here at -4. And there we go. There's our cosine reflected over the x-axis with that amplitude of 4. Again, like I said, today is actually the process of graphing these is not too crazy because we aren't changing a ton about them. We're just shifting it or stretching out or shrinking our functions and then reflecting them. But every single day we're going to add on a little piece, and it's going to be pretty going to make it more complicated. So at the end, we're going to be looking at like a massive sine and cosine function where we have a ton of different transformations. So it's important to keep track each day of all these transformations and the process to do them. So that way when we add on, you're not getting lost in the steps beforehand.